In this video series, we'll be looking at the concept of phasors and how they are made. But first, let's take a look at a simple sine wave. Let's make a right angle triangle, and the base is known as horizontal, the height is known as vertical, and the hypotenuse, which we call diagonal. And let's say that the length of the diagonal is 1. So I can say that sine of this angle theta is vertical upon 1, or the height upon the hypotenuse. So if I increase the angle theta while keeping the diagonal equals to 1, so obviously this thing is going in this fashion, the diagonal, and if I watch the length of the vertical, let's say theta equals to 0, the vertical is obviously going to be 0. If theta is, if this height is at maximum, the theta is obviously going to be at 90, and if this height is going to be like here, that will again be 0. The theta would be 0 at, or the sine theta would be 0 at angle of 180, and at 270 degrees the sine would be at -1, and at back to 0 we are back to 360 degrees. So I can just write this function as g of theta, function name, the g of theta equals to sine theta. That's the function of theta. If we say that the length of the diagonal is a, right now we had the length of the diagonal equals to 1. Therefore, the maximum amplitude of the sine wave was 1 and -1. So if I write this thing as a, the g of theta would become a sine theta. Here it was simple 1 sine theta. Now, if we look at the speed at which this theta changes, and then we know that the velocity is equals to distance upon time, but we cannot use the velocity formula because every point on the diagonal is traveling at a different speed. So if I'm standing over here, I'm covering the most amount of distance while rotating this thing. If I was standing at this point, I'm covering the least amount of distance. So I cannot use this formula distance over time for velocity whenever we are talking about some rotational stuff. So we define a new term, something known as angular velocity. It is represented by omega, and that is equals to theta upon time, or angle upon time, or the unit of this omega is degrees per second. So I can write theta equals to omega t. Now we had the original function of g of theta equals to a sine theta. A was the length of the, or the amplitude, and now we can write theta equals to omega t. So this function becomes g of t equals to a sine omega t. That means this omega is for a simple single sine wave. This omega is a constant quantity, and it becomes a time domain function, that if we write this thing as, let's say, a simple sine wave of 1 hertz, 1 hertz is the time period is 1 second, and the angular velocity omega equals to 360 degrees in 1 second. And let's say if we have a frequency of 3 hertz, omega is 360 degrees into 3, that is, it's covering 1080 degrees per second, and the time period is obviously 1/3 of a second. If we have a frequency equals to 2 hertz, a sine wave, then I can write t equals to, the time period is half of a second, and the omega equals to, it covers 360 degrees twice in a second. So we can just write omega, or angular velocity, equals to 720 degrees per second. So here the unit of frequency is given as hertz. Hertz was the name of some person, but the original unit for this frequency was cycles per second, CPS, and that is actually much more explanatory, because if I have a 2 hertz or a 2 cycles per second sine wave, that means this diagonal is covering 1 and 2 revolutions in a second, and that's how we get a 2 hertz sine wave, or 2 cycles per second sine wave. So omega here is 720 degrees per second, so we can write this thing as omega equals to, here it was 1 hertz and omega was 360 degrees per second. If frequency was 3 hertz, we could have written 360 degrees into 3 per second, or if frequency was 2 hertz, we could have written 360 degrees into 2, 720 degrees per second. So we can just write omega equals to 360 degrees into f. Now we know that frequency is inverse of the time period, so we can write omega equals to 360 degrees into 1 over t. Now let's consider a circle with radius r, and these things are, this is a radius r and this is a radius r, and we make an arc length so that this arc length is also equal to the radius of the circle. So the whatever angle we get here, that is known as angle in 1 radian. Okay, so how many radians can we make if we divide the circle like a pizza? Then there are plus a little extra radians in a circle, or we have circumference divided by the radius equals to radians in a circle. So the circumference of the circle is 2 pi r divided by radius. So we can say that we have 2 pi radians in a circle, or 2 pi or 6.28 radians in a circle, or 360 degrees in a circle, because we know 2 pi equals to 360 degrees. So we can just write omega was 360 degrees into f, so we can represent omega equals to 2 pi f, and that's how we get sine omega t for gt equals to sine omega t, and omega equals to 2 pi f. And we are assuming that this sine wave is starting at 0 degrees, and if this sine wave was starting at some other degrees, such as 45 or maybe 90 degrees or 100 degrees, so we would have written sine omega t plus theta, or sine omega t plus phi, or any angle, so that we have a starting angle or a phase angle at t equal to 0. Similarly, if we watch the horizontal length of the horizontal while rotating the diagonal, we get a cosine wave. If the diagonal is at the 0 degrees, the cosine is maximum, the horizontal is maximum. If the diagonal is at 90 degrees, the horizontal is 0. If the diagonal is at 180 degrees, the cosine is at maximum, but like -1. If the diagonal is here, the horizontal is going to be 0 again, and that's how we get the a sine or a cos omega t. A is the length of the diagonal, and if this cosine wave is starting at 0 degrees, and that's here cos of 0 is 1, we write cos omega t. If this cosine wave starts at some other angle at t equals to 0, then we write cos omega t plus some angle. That is the phase angle. So the first term is written as in radians traditionally, and the second term in electrical engineering is written as degrees if it has a phase angle.